Welcome to week 3 of the AI planning course. In week 1, we've already seen an informal introduction to the planning problem we're trying to address in this course, and we've seen some of the context in which planning takes place. In week 2 then, we've seen two main things. We've seen search algorithms and we've seen the STRIPS planner. For search algorithms, we first talked about heuristics and how they encode knowledge that helps us guide the search. And then we've used this knowledge in the A-star algorithm for graph search. Finally, we've talked about how to find good heuristics, as good heuristics are vital for the performance of the A-star algorithm. Then we've moved over to the STRIPS system. The STRIPS system gave us the STRIPS representation, which describes operators as consisting of preconditions and effects, and the effects are often divided into an add and a delete list. Then we've had a formal definition of the planning problem we are trying to solve in this course, and we've seen some algorithms that we can use to solve this problem. The first algorithm we've seen is forward state space search, and then we've described a variant of that, which is backward state space search, both searching the same state space. In addition to all this technical material, we've shown you some features. In week 1, we had a feature on planning for robots, and in week 2, you've seen a feature by Nils Nilsson on the A-star algorithm and the STRIPS system they developed at SRI. In this week, we will have another feature, and I hope you'll enjoy this.
So far, in our search for solutions to planning problems, we have considered plans that were sequences of actions. They may not have achieved the goals, but they were plans in their own right. In the first half of this week, we're going to look at a different search space that consists of partial plans. Partial plans still consist of the same types of actions we've seen previously, like the move action here, or this move action, or the load action here. So they are the same actions. What is new is that we explicitly record the rationale of why we have an action in a plan. For example, here we see that we have an effect of this action, and we're using this to achieve the precondition of another action. And we've introduced this link here to record this fact. Also, we have explicit ordering constraints, something you see here and here, that tells us in which order we have to execute the actions. That makes it possible for us to have partial plans that include a partial order, so actions can be in parallel. Finally, partial plans may not have fully instantiated actions. Some of the actions may contain variables. That is something I've already mentioned during lifted backward search. That is possible, and in partial order planning, that is usually done. A planner that searches the space of partial plans is the UCPOP planner developed in the early 90s, and we will see the pseudocode for this planner later in this segment. In the second half of this week, we're going to do something completely different, namely, we're going to change the planning problem that we are trying to solve. So far, our planning problems consisted of, amongst other things, a goal, which defines a set of goal states. In the new type of planning we're going to look at here, we're not trying to achieve goals, but we're trying to accomplish tasks. Tasks can be seen as high-level descriptions of activity that we want to execute, but they're so high-level that we don't know how to directly do them. So the approach we're taking, usually, is to break them down into smaller tasks. And we do this until we reach a level where the tasks are so small that we have an operator in our planning domain that directly accomplishes this task. For example, the first subtask here that we have in this decomposition tree that decomposes our overall tasks into smaller tasks would be to take something with a crane, etc. And we've already seen that our planning domains contain operators that can directly accomplish these so-called primitive tasks. And that is the approach we take in hierarchical task network planning, or short HTN. A lot of practical planning systems take this approach, as you've already heard my colleague Austin Tate tell you in week 1. We will look at a slightly simplified version of this problem called STN planning. This will be described in detail but then I'll describe what is different about HTN planning. And hopefully you will understand that the power of HTN planning largely comes from the fact that it handles constraints on world states explicitly. And since there are many different types of constraints that can be handled, HTN planners can be adapted to specific applications.
So, now, before we start with the technical material for week 3, I want to again remind you of the social platform that comes with this course. There is the discussion forum, which you can use to post questions and get help. And there's also the course wiki that you can use to collect useful information. Please make good use of them.